10.3 is composite functions. Woo! What does composite mean? We could have composite decking, which means that it's material that's been made up of more than one material. Composite functions is when we have a function that's the result of more than one function being put together. So in this example here, we have g of x being put in as the argument for f of x. We would say this is f of g of x. Now some people like to write it with an open circle, so it means the same thing as this. A bit more unclear. This is very clear. I think more students have trouble with this notation, but it's open circle, and that's why it's very important if we want multiplication that it's clearly a closed circle. And if we want composite, if we're putting g of x inside of f of x, we want that to be an open circle, kind of like there's a open space for g to hop into. Now the domain of this is going to be very interesting. So first of all, our domain for this, the x values need to fit into g of x. Now g of x does its thing and returns what would normally be y values or its output, and that becomes the input or the arguments for f of x. So the domain needs to be in the domain of g of x first, and then the y values or the output of g of x needs to be in the domain of f of x. Example 1, we have f of x, g of x, and h of x given. We want to make these following composite functions. So the first one here, we've got f of g at -2. So the first way I'll do this question is breaking it apart. I'm going to take the g at -2 and determine its value. So g -2. I look up here for the g of x function. So it's 4 times the absolute value of -2, which is 8. And now I use this as my input for f of x. So f at 8, we look up here for f of x, and that's just 3 plus 8, which is 11. And so the value of this composite function here, f of g at -2, is 11. Now I didn't need to break it apart. If you find the equations are very long, you might want to break it apart into 2 just to make it clear, but you could do this question together. So I'm going to write or here to show a different way. You can keep it together and evaluate essentially this inside of the brackets here. So g at -2 is 4 times the absolute value of -2. And just do the math inside these brackets. So f at, and this turns into 8 as we've already seen, and f at 8 is 3 plus 8, which is 11. So I'm going to continue to do it this second way. I find it's very clear and it keeps everything neat and tidy. So we got g is the outer function, f is the inner. See, it's in the same order. So g, and then inside here is f at -2. So this is f at -2. And we evaluate that, get 1, and then g at 1 is just 4 times the absolute value of 1, which equals 4. Let's do this one. Now we've got triple layered. So we've got h, g, and f at -4. So here's f at -4. It would look like this. H is just patiently waiting until the inner functions are done their thing. G at -1. G at -1 is just this here at -1. Which equals 4. H at 4 is this thing. So 4 squared minus 4 is 16 minus 4, which is 12. Next example is g is inside now. So we've got h and g at negative 4. It's 4, absolute value of negative 4, which is 4 times 4, so it's 16. Now we've got h at 16, which is 16 squared minus 16. That is 256 minus 16. That turns out to be 240. Last one, 3 layers again. We've got g of f and h at 3. So that would be 3 squared minus 3. Which is 9 minus 3 is 6. So now we have f at 6. F is 3 plus x. 3 plus x. Now that gives us g at 9. And g is 4 times the absolute value of x. So 4 times the absolute value of 9, which is 36. Example 2, we have f of x and g of x given here. We want to make these composite functions, and we want to find their domain and range. So f is our outside function here, and g of x is going inside, so g of x is negative x squared. That's going to become our argument for f of x. Wherever we see an x in f of x, we're going to replace it with this, negative x squared. And that's it. That's our function. We cannot simplify this further. Don't you dare try to take the square root of individual terms. Now, our domain is going to be dependent on this radicand. So the radicand needs to be greater than or equal to 0 to keep everything real. And this is a quadratic, and we can solve this graphically. We can easily picture what this thing looks like. It opens down and its vertex, or it's been translated up 1 unit, so its vertex is at 0, 1. It's got x-intercepts at -1 and +1. Where is this quadratic greater than or equal to 0? Well, in between -1 and +1. So the domain for this would be -1 to +1. Now we could also do this algebraically. Let's add x squared on both sides. And then we get x like this. X is less than or equal to 1. Take the square root of both sides. And we get 1 on this side greater than or equal to, and if we take the square root of a variable squared, we're going to get plus or minus x. Now we've got 2 cases here. One is the plus case and one is the minus case. We want to split those 2 cases up when we're doing this algebraically. So one is greater than or equal to positive x, or x is less than or equal to 1. The other one needs a bit of work. It's 1 is greater than or equal to negative x, and we've got a negative, so let's multiply by -1 on both sides, and that turns into -1, and then we got to flip this inequality. That turns into that. So you can see it's less than 1 and greater than -1, which is what we had already from the graph. Now for the range, if you looked at this graph here and we were taking the square root of this quadratic right here, our minimum would be 0. The square root of 0 is 0. And our maximum would be 1, and the square root of 1 is 1. And if we're taking square root in between 0 and 1, we know that it's going to give us back a larger value. So the graph of this is actually more of a bubble here that has invariant points here and here, bubble around here and on the other side. So our range is from 0 to 1. Next one, we've got the opposite happening. We've got g, and this time we're going to put f of x inside of g, and f of x is this whole thing here. So everywhere where we see an x in g, we're going to replace it with this radical. So we've got negative, and here's our x. We're replacing it with this radical squared. And we can simplify this. Negative square and square root will cancel out, just give us x plus 1. And that's fine, or if you want to get rid of the brackets, that would also work there. Now our domain and range for this question. You might be tempted to just look at this and say it's a linear function, so x ER. But it's not this. We simplified it to this, but we can't forget where we came from, so we look back here. And we've got this radicand that needs to be greater than or equal to 0 to keep things real, which means that doing a bit of algebra, x needs to be greater than or equal to -1. So that's our domain. -1 is our smallest value, and infinity is our largest value. And the range for this. If -1 is put in here, then this is 0, squared is 0, squared is still 0, negative is still 0. So our smallest range value would be 0. You can also check this graphically using your graphing calculator. The next point is if x goes off to infinity, then we've got infinity going on here, and the square root of infinity is still infinity squared, and so infinity. Example 3, we are given that h of x is a composite of f of g of x. Now we're given h of x, and we're not given the two that make this composite, so we want to determine that. So in this one, looks like, there's an x minus 2 here, and there's an x minus 2 here. That might be our inner function that got put in here. And our inner function is g of x. So, you know what? Let's say that g of x is x minus 2. And f of x is, well, this thing right here was replaced, and this thing right here was replaced, and so that should be our x. So the x minus 2 is being put in there for x and is being put in there for x. So that's a potential answer. Next one. Our inner function here is g, and it could be this part, x cubed plus 1. And our f of x could be just the square root of x. And so f of x is our outer function, and this x right here is being replaced by g, which is this whole thing here. Now this isn't the only answer. Some of you might have said, hey, but g of x could be just the x cubed part. And f of x, well, that could have been x plus 1, so that when this x is being replaced by x cubed, then we end up with this. So, unless they give you some hint, or maybe it's multiple choice, there could be more than one potential answer for these questions. G of x is the inside function, and f of x is the outside function. What could be the inside function here? Ooh, I don't know, maybe x squared? And this could have been x minus 1, so that when we replace x with x squared, it looks like this. Or g of x could have been just x. F of x could have been x squared minus 1. And you might be able to think of some more for these. Example 4 is a word problem. A spherical weather balloon is being inflated. The balloon's radius r in feet after t minutes is given by r equals the square root of t. Express the volume of the balloon as a function of its radius. And that's how we normally do it, so this isn't a problem. Volume equals 4/3 pi r cubed. Now I'm just going to use function notation because with composite functions, it'll be easier to use. Function notation, this same equation here looks like its volume is a function of its radius, and it's still the same. Now remember, this is not v times r. This is v of r. So that's its variable. We're declaring its variable in function notation. We want to express the volume of the balloon as a function of time. So we have r in here as our variable, and we want it as a function of time, t. So we really want to make our composite function. We've got this, v, and then we want to replace it with this. And this in function notation would be r of t equals the square root of t. So this is function notation. It means the same thing as that. All right, so v of r of t, and we're going to replace r with r of t, which is that. And that's okay if you want to mix radical and exponent. Say we didn't, say we wanted it just in exponential form, then t3 and the index of the radical becomes the denominator of the exponent. And there, we've got a volume as a function of time, which may be helpful. Maybe we want to calculate how long the volume it will take before the volume is a certain amount or something. After how many minutes will the balloon's volume be? 4,000 cubic feet. All right, so volume is 4,000, and we want to find the time. So times both sides by 3, divide both sides by 4. And we get 3,000 pi t. Then divide both sides by pi. So 3,000 divided by pi is equal to t power of 3 over 2. And then we want to square both sides and cube root both sides, or essentially get rid of this. So then I'll flip it around. So we could do 3,000 over pi. And we want to square both sides and cube root both sides to get rid of that. Okay, and we can try to simplify this. We've got 3,000. We can split that up into 3 times 1,000 over pi. Looking for that perfect cube. We can, 3 is not, 3 to the 2/3. Cube root of 1,000 is 10. 10 squared is 100. So we can simplify it like this. I don't know if that's any better though, but it's always worth trying. It's not going to be a rational number here anyways, just because there's pi involved, and also the cube root of 3 is going on here. So if we just take a look at the decimal approximation of that, it's 96.97, and that is pretty much 97 minutes. So it would take 97 minutes for this balloon's volume to be 4,000 cubic feet. Example 5. A cylindrical tank is being filled up with water. It's got a radius of 50 centimeters and it's being filled up at a rate of 5 liters per minute, or 5,000 cubic centimeters per minute. Find the equation of the height of the water with respect to volume. Now normally when we're finding the volume of a cylinder, it's area of the base, pi r squared, times height. And we want it the other way around. We want the equation height with respect to volume. So I'm just going to do some algebra here. Divide both sides by pi r squared. We get height is equal to volume divided by pi r squared. Now the next thing we can do is the volume is changing. We're adding more and more water, and so that's a variable. The height is also changing. As we add more water, the height will increase, and that's a variable. Radius is not changing. No matter how much water is in here, the radius will always be 50 centimeters. So we can actually use 50 in place of r and get rid of that. So we've got h. Our variable here is going to be v. V over 50 squared is 2500 pi. And there's our equation, height with respect to volume. Next one, we want to find the equation volume of water with respect to time. So volume and time are both changing here. Our variable will be t. Now we are putting in 5,000 liters of water for every 1 minute, and so t will be time in minutes. And last, we want to put these equations together. We want the height of the water with respect to time. There's height, but it's with respect to volume. And there's volume with respect to time. So if we can make a composite function, we can actually get height with respect to time. And then think of the possibilities. I mean, we could be some evil villain drowning a superhero, and we could calculate how long it would take. So we've got h here. I'm going to make a composite by putting this inside. We've got h, v of t is just 5,000 t. And now we can put that value everywhere where we see v, which is 5,000 t over 2,500 pi. And simplify this. Looks like we got 2t over pi. This was RF1 function operations. We were doing composite functions. Here's some homework. Give it a try. Have some fun. See if you know what you're doing.